let's get started. Welcome back to machine learning. So let's get started with some administrative stuff. So as I'm sure you all remember, the first batch of online questions is due tonight. If you didn't remember that, go download them from Piazza, fill them in. The link is it's on the announcements page. Next batch of online questions is going to come out today. I'll post it sometime after class, so look for that link on Piazza. Homework 1 is due on Thursday. Hopefully all of you knew that already. I know a very large number of you do know that because you've been hitting our AutoLab servers very hard over the weekends, which is great. Yeah, so if you have any questions, keep asking them on Piazza. Let us know what's if you run into any difficulties. And we're planning to release the solutions to homework 1 after Thursday plus the max number of late days that anybody takes. So we'll post those on Piazza when they're available. All right, so today we're going to go back to the Perceptron algorithm, spend some time with our good friend. Just to remind you, this is what the Perceptron algorithm is, very simple. You start off by setting your weight vector equal to 0, then you cycle through your training points, and for every point you predict the sign of your weight vector dot with that example. And if you're right, good. And if you're wrong, you update your weight vector. You update it to be the new weight vector is the old weight vector plus the signed training example. All right? Yes?
Just really quick back to the server problems. Do you think that the servers might go down as we approach Thursday?
I hope not. The only server problem we've had that I know of is the fact that it was slow for 45 minutes when we updated it to hopefully increase everybody's score. We don't plan on doing any updates in the 10 minutes before the deadline on Thursday, unless somebody points out a severe problem to us. And if something like that happens, we would extend the deadline. Any other questions about the homework or procedures for the homework? All right, so Perceptron algorithm. Does everybody remember the Perceptron algorithm? Everybody familiar with it? This rings a bell? Yeah, good. OK, so what are we going to do with the Perceptron algorithm? We're going to analyze it, right? We want to figure out what it does. And this is good for two reasons. First, we're doing it so that you know what the Perceptron algorithm does. But maybe as a even more important or high-level thing, we're doing it so that you get an example, a first example of how to analyze machine learning algorithms, right? So the general pipeline when you hit a new problem is, well, if there's some existing software or algorithm that fits your purpose, that's great. But as we said a while ago, a few lectures ago, if you're not in that lucky situation, you're going to have to design a new machine learning algorithm for the purpose. And to do that, you would use the algorithm design principles that we described to you and will continue describing to you in these lectures. So things like maximum likelihood estimation, the Bayes rule, empirical risk minimization. And OK, so you apply one of these principles, maybe several of these principles, and you design your algorithm. Now you want to know, is it going to work? Or if it's not going to work, how is it going to fail? So what the heck is it going to do when it actually hits the data, right? And so in order to do that, we have to analyze it. And the sort of questions we're asking when we analyze it is, what does it converge to? Like if it has a weight vector, does that weight vector converge to some W star optimal weight vector? How fast does it get there? Are you going to need 10 examples or 1 million, right? Are you going to need 10 milliseconds of computer time, or are you going to need a million days, right? Obviously, these are pretty important things to know if you're going to use your algorithm in practice. And so to answer these questions, the way to approach it is just to try a bunch of different machine learning analysis principles. And we're going to be showing you a bunch of them throughout the semester. The one we're going to be using today is called amortized analysis. And we met it briefly last lecture, but we'll meet it in much more detail this lecture. Another one is tail bounds. You'll be seeing those later in the semester. And there are lots more that we'll mention at the appropriate times. All right? So that basic idea makes sense to people? Yeah? OK. So oops. Right. So just to actually going back here for a second, amortized analysis, like we mentioned before, the basic idea is that sometimes it's hard to bound how often something bad happens. Specifically, it's hard to bound how many times it'll happen on every trial, right? So making a mistake, well, any given trial, you could make at most one mistake, and it's difficult to get a tighter bound than that. But we want a tighter bound. So what do we do? What we do is we try and bound over the long-term average how many mistakes we're going to make, or what the rate is of making mistakes over the long-term average. And in order to do that, what we'll usually do is use a potential function to keep track of the changes in state of our algorithm. And so we'll see an example of that later. Tail bounds, again, we'll go into much more detail on those later. But the idea is that, all right, if you draw one example, you might get unlucky with it, right? Like, for example, suppose you're trying to estimate the class conditional mean for a naive Bayes classifier, right? You draw one example, well, it could be a long distance away from the mean. You draw another example, it could be a long distance away from the mean in a different direction, right? But if you draw a lot of examples, the probability that they're all off in the same direction has to go down, right? And it has to go down actually pretty fast. And a tail bound is basically trying to bound that probability. It's called the tail bound for that reason. Basically, the idea is that if you have a probability distribution that looks like that, right? So here's the mean of that probability distribution. And the tails of the probability distribution are the stuff off, well, way away from the mean, right? And so a tail bound is trying to bound the probability that you land in one of those tails. OK? So that's a tail bound. And again, we'll see more of those later. So all right. So now let's get back to the perceptron. And I just want to remind you, we went over the proof very quickly at the end of last lecture. It might have gone by kind of fast, so I want to go over it and make sure that everybody is good with it. So the first component of that, the first component of analyzing the perceptron was the idea of a margin. And so a margin, the picture is easy. It looks kind of like this, right? We have a plane that's passing between our examples, and the distance, some of our examples are close to the plane, some of them are far, right? And the distance of a given example to the plane is called the margin of that example. And the margin of the plane is the margin of the worst case example, the closest example to the plane. All right? So in formulas, that looks like this. What we want to do is solve this optimization problem right here, right? So this constraint here says that I classify the example correctly with a given margin. And the margin actually winds up being, well, the longer the weight vector, the larger that dot product is going to be, all other things being equal. So if you make the weight vector, if you have to make it really long in order to satisfy that constraint, you have a small margin. And if you can make the weight vector really short and still satisfy that constraint, you have a big margin. And in particular, the margin is 1 over the length of the weight vector when the weight vector solves that optimization problem, right? And we proved that in class the other day, but just briefly. Right? So the weight vector is the normal to that hyperplane, right? So that's the weight vector W. I guess I'm not really drawing it. This is the case where we have an intercept, but I guess the weight vector is still the normal. So in order to, the margin is basically the length of the projection of the example onto the weight vector, right? So it's the margin of a given example is ui dot w over norm of w, right? That's the projection of ui onto the weight vector w. And in order for that to be bigger than or equal to gamma for all I, well, that's the same as saying ui dot w is bigger than or equal to gamma times the norm of w, right? And so if we want this to equal 1, right? If we want that to equal 1, then the norm of w has to be at least as large as 1 over gamma, right? So that's a proof that 1 over the norm of our weight vector is a representation of the margin. All right? So, all right. So now, based on that idea, we did the perceptron proof. And this is the slide. This is the same slide you saw at the end of the lecture last time. In case you don't remember it, we can go over it again. So basically, the idea is that, so we're going to start assuming that our examples satisfy our margin, right, like that. Margin constraint, right, and that means that the margin is bigger than or equal to 1 over the norm of our weight vector. Okay, and so what we're going to do is we're going to look at two different quantities: the norm of our weight vector and the dot product between our weight vector and the optimal weight vector, right? So W is our current weight vector of the perceptron algorithm, and we're going to look at its norm and its dot product with W star. Why are we going to look at those two? Well, because the is going to work out, but how could you have guessed that? Well, so one thing would be, okay, if the norm of W is getting big, that's bad, because we only change W when we make a mistake. And so in order to weight vector be big, we have to be making a lot of mistakes, right? So that's what we're interested in when analyzing the performance of the algorithm. For W dot W star, right, so if we have our weight vector W star is pointing off in some direction, if our weight vector W is pointing in completely the opposite direction, meaning a really small dot product, a really negative dot product, that seems like a bad thing. If it's pointing in almost the same direction, right, then that's probably a good thing, right? So the dot product between W and W star also seems like a reasonable thing to use to measure the progress of our algorithm. Okay? Everybody with me so far? Yeah, I see some nods. That's good. Okay, so let's analyze both of those things. Let's start with the norm of our weight vector, right? So if we have the norm of our new weight vector, squared, just to make it easier, is going to be the dot product with itself, right? And the new weight vector is, let's suppose we make a mistake, then it's W plus UI dotted with itself, right? So we expand that out, W dot W plus 2 UI dot W plus UI dot UI, right? And UI dot UI, we're assuming that all of our examples are normalized, so that's bounded, right? And we assumed we made a mistake, which means we misclassified this example, right? Which means that the sign of UI dot W is negative, right? Because if UI dot W is negative, then we'd be on the correct side of the hyperplane, the decision surface. Okay, so that's less than or equal to 0, right? And so that means that, and then this here, right, is just the squared norm of W. So the new squared norm is the old squared norm plus 1. It's at most that, right? And that happens on every mistake. So if there are m mistakes, we get that the squared norm can't be any larger than the number of mistakes. Okay? So questions on that part of the So the other part, right? So now let's analyze the product between weight vector and W star, right? So for the new weight vector dot W star, again, let's suppose that we made a mistake. So the new weight vector is just the old weight vector plus UI dotted with W star. You distribute the addition and multiplication, so you get the old value of W dot W star plus UI dot W star, right? And so this is now, oh, there's a mistake in this slide, right? So UI dot W star, UI has norm 1, W star has norm W, right? And so this should be not 1, but W, right? The Cauchy-Schwarz inequality says that the dot product is the product of the norms, right? And so after m mistakes, W dot W star is less than or equal to MW. W increases it increases by at most W on each mistakes. If there are most m of them, it goes up to at most MW. Yeah?
Is it really 1? Because we have that UI dot W star satisfies the equation on the first line.
You're right. UI dot W star is at most, is at least 1. Yes, that's right. OK, good. So thank you. Let's get rid of, luckily those were the last ones that I wrote, so they vanish without a trace. Thank you for catching that. Right, so I could in fact make the bound that it's less than or equal to the norm of W, and that would be using Cauchy-Schwarz inequality, right? That would have been correct. But because I have, like you pointed out, I have this inequality, I can use that instead and get a tighter bound that it's bigger than or equal to 1. Right? And again, that happens only on every mistake. So if you increase by 1 for every mistake and you make m mistakes, right, this it's bigger than or equal to m. Right? Increase by at least every mistake, it's at least m. Okay. So then the last thing that we can do, right, is combine these two things, right? So this here, right, tells us that m is less than or equal to W dot W star. Now I'm going to use the Cauchy-Schwarz inequality. W dot W star is less than or equal to the norm of W times the norm of W star, right? And then the norm of W star is that's defined to be equal to W, right? Capital W, right? That's the same as that. And then the norm of W is less than or equal to the square root of m from this equation that I proved earlier, right? And so the whole thing is less than or equal to the square root of m times the norm of W star. All right? And so now I've got an equation, an inequality that says that m on one side is less than or equal to the square root of m times W, right? And so if that gives me this equation right here, right? Divide through by square root of m, or m is less than W squared, right? So the number of mistakes we make can't possibly be more than the square of the length of the optimal weight vector, right? Now that's a pretty strong result, right? A finite number of mistakes, even if I get infinitely many or arbitrarily many training examples. But it required some pretty strong assumptions, right? The examples had to be linearly separable. That's what this constraint means. And they had to be linearly separable with a positive margin. That's what the length of the optimal weight vector means. All right? So does everybody feel comfortable now with the perceptron proof? Yes? Cool. So you might ask a bunch of questions like, OK, what happens if things aren't linearly separable? Or what happens if you change the algorithm slightly? And we'll get to those questions in a few slides. And they'll basically wind up being minor modifications to this proof. So if you don't understand this proof now, we're going to be seeing it again. So ask me some questions. All right. Do you understand as well why it is that we were interested in doing a proof like this? This is a quiz from 20 minutes ago. Why are we interested in doing a proof like this? Anybody? Do you not remember, or are you just scared to raise your hands? Right, so we're demonstrating amortized analysis. That's a good answer. Let's bring it up one level. Why would we care about amortized analysis? That's true. We can solve this particular problem using amortized analysis. That's a very good reason to care about it, to the extent that we care about perceptrons. How about other machine learning algorithms? Yeah? Right. So the idea is that this is a proof technique that we can use not just to analyze this one particular algorithm, but there are other algorithms that use the same proof technique in order to analyze them. And so if you were trying to figure out what they did, you would want to know this proof technique. All right? In case you're interested, an example of one of those algorithms is weighted majority. We're not going to, I don't think, cover that particular algorithm later in the course, but if you want to see another example of this proof technique, you can Google weighted majority, also called multiplicative weights, and you'll see a proof like this in the literature. All right. All right, so here's what the bound looks like if we have a weight vector of norm 3, right? So the bound, if you remember, was that and the bound was that come on. All right. Technology seems to be failing me again. The bound was that m had to be less than the square root of m times w, right? And so the two lines in this graph are m and the square root of m times w for different values of m. And I'm assuming that w is 3 in this case, right? And so what the bound says is that m has to be in a region where the curved line is higher than the straight line. Right? That makes sense? And so in order to achieve that, right, we have to be just in the region on the left graph, right, where u is less than or equal to 9. Right? And so that's what the bound looks like. And our potential function, right, is basically, right, if we want to think of this in terms of a potential function, right, we had the inequalities w dot w star bigger than or equal to m and the norm of w squared less than or equal to m. And right, and in order to think of this as a potential function, what we're going to do is I'm going to pick the potential function q is equal to the norm of w minus w dot w star scaled by the norm of w star. And I already said why these two quantities make sense to have in the potential function. They're opposite signs because it's bad to have large w and it's good to have large w dot w star. And so basically it's bad to have high potential and good to have low potential. And so we can put bounds on this potential function, right? The potential function basically records the state of our algorithm, and we can put bounds on its value. So for example, 0 is less than or equal to q. Why is that? Because, well, this here is a unit norm vector, and so w dot that vector is less than or equal to the norm of w, right, which cancels that term. And so it's bigger than or equal to q. Q is bigger than or equal to 0. But we also then, on the previous slide, or using these inequalities, right, can show that q is bounded by m, the square root of m plus square root of m minus m over w, using those two inequalities, right? And so we placed bounds, right? As our algorithm progresses, it changes its potential function. We placed bounds on upper and lower bounds on how much the potential function can vary. And using those bounds, we can then back out a bound on what can happen during the course of the algorithm. All right? So that's sort of the general flavor of amortized analysis. You put state changes into a potential function, bound how it can vary, and then use that to get the bounds on the quantities that you care about. All right? All right, so now let's let's go to the non-separable case, right? So this is going to be potentially a lot more interesting, right? Because I don't actually encounter too many linearly separable data sets in practice, but I do encounter data sets where a line is a pretty decent separator. It has a few errors, but it's not going to, it's not going to be perfect. All right. So how would we analyze this? Well, so the first thing we could do is just try to directly bound the number of mistakes that we could make, right? The problem is that it actually turns out to be very difficult to prove any bounds directly on the number of mistakes we make, because optimizing the number of mistakes is a computationally very difficult problem. It turns out to be NP hard to find, for example, the linear separator that has the fewest mistakes on your training set. So that's a pain to analyze that. So what's the next best thing? We'll get some quantity L that we'll call a loss function, and we will arrange it so that L is bigger than or equal to the number of mistakes that we make, and then we'll try to bound L instead, right? So what we're going to pick here is a pretty famous loss function that a lot of you may have seen already, right? It's called the hinge loss. It looks like this, right? It's if we have, so we're going to apply the hinge loss to our dot product between the weight vector and the training example. And if that's bigger than or equal to 1, we get that example right. And so we get a loss of 0. And then we'll say that the loss increases like this, right, as we get farther and farther on the wrong side of the margin, right? So the loss is 0 if we get the example right with a big enough margin, and it increases linearly past that. And this is interesting because, OK, we're getting the example right over here, right? And then we're getting one mistake over here, right? We get the example wrong and get one additional mistake. And so if we just think of that as the misclassification error, right, the number of mistakes we're making, the hinge loss is an upper bound on the number of mistakes we're making. Oops. I should draw that actually at 0, not at, let's see if I can make that. Right, so it's one mistake here, and it goes down to 0 here, and it goes like that across the rest. All right. So does that make sense? Yeah. So we're going to pick that because it's an upper bound, but also because it's a much nicer function to work with, right? So if you remember the idea of convexity, right? Convex functions are the ones that look like that. Non-convex functions, might look like that, for example. So convex functions are going to be much easier to work with, much easier to analyze. And so the hope is that using this bound, we're going to be able to actually prove something in the non-linearly separable case. Make sense? All right. And now, this thing here, right? This quantity right here, L, which is the sum of this loss function across all training examples applied at our actual weight vector that we have at that point in the algorithm. This is called the risk. And in particular, because it's the risk on a training set, it's called the empirical risk. And trying to make the empirical risk small is called empirical risk minimization. And that's the reason for the name of this class of algorithm design techniques. That you're going to pick some sort of representation of loss, evaluate it on your training set, and pick a parameter vectors in order to make that empirical risk small. Okay. So in particular, just to connect back to what we were saying earlier, if the empirical risk is 0, what does that mean about our algorithm? It's made no mistakes so far. That's right. It means actually a little bit more than that, right? It made no mistakes so far and something else. So it's something about the margin, right? So in order to get empirical risk 0, right, we have to separate every example. Every example has to satisfy, right? So if we have L equals 0, that implies every example satisfies ui.w is bigger than or equal to 1, right? And so that then means that we have a margin that's at least 1 over the norm of w, right? So this is a strict generalization of what we were doing before, right? If we constrain our empirical risk to be 0, right, or if we constrain the risk of, let's say, an optimal weight vector W star to be 0, that means that everything is perfectly linearly separable and it has a margin at least 1 over the norm of W star, right? But now it's going to be more general because we're going to allow violations of the margin constraint, right? You're not going to get infinite loss if you're on the wrong side of the margin. You'll just get loss that increases depending on how far you are on the wrong side of the margin. All right. So let us see if we can analyze this. So now we're going to suppose now that some unknown optimal weight vector W star here, right, has now not a perfect linear separation, but linear separation with some errors, but with a margin, right? That's what this means, right? This means then that we have margin 1 over the norm of W star, except for a few errors. And it actually means something slightly stronger than only a few errors, right? It means only a few margin errors, only a few points where we get on the wrong side of the margin. And it also means that none of the margin errors can be too huge, right? So if the sum L star is bounded, that means that we can't make huge margin errors on any individual training points, right? So this is a weaker assumption than we made before, right? Before we assumed perfect linear separability. But it's a stronger assumption than just that there exists some weight vector that classifies the points well, right? And in fact, it would be very difficult to learn only under the assumption that that there was a weight vector that classified the points well. All right. So if you remember, we had the hinge loss, which was h of z is equal to max of 0 and 1 minus z, right? And the hinge loss satisfies, well, it satisfies h is bigger than or equal to 0, right? Because it's the max of 0 and something else. And it also satisfies h is bigger than or equal to 1 minus z, again, because it's the max of 1 minus z and something else, right? And then this is the same as saying that z is bigger than or equal to 1 minus h of z. All right? So let's analyze. So on the, I guess the first thing we want to say is that we're going to analyze the same quantities that we did before, almost. We're going to analyze the norm of W, and we're going to analyze W dot W star. But this time we're actually going to, we're going to analyze the norm of W star. And the analysis for the norm of W turns out to be exactly the same as it was before, except that now M counts margin errors instead of errors, right? No, I'm sorry, M still counts just plain errors. And so we're going to, yeah, just counts just plain errors. And so on, right, and so on an error, So on an error, the norm of W is going to turn out to behave exactly the same as the way it behaved before, right? The analysis is going to carry over with no change, and we'll get that the norm of W squared is less than or equal to m, right? That's the bound that we had from the previous analysis. And here m is the number of mistakes. If we try to analyze this other quantity, right? So that analysis is going to be slightly different, but it's not going to be very different. So let's take a look. So we get that then W new dot W star is equal to, well, on a mistake, W new is W plus UI dot W star, right? And so that's equal to W dot W star plus UI dot W star, right? And so now the only change is that we're going to bound UI dot W star a little bit differently. So remember, that's the value of our discriminant function, ui dot w or ui dot w star. What we do now with our discriminant function is we put it in as an argument to the hinge loss, right? If it's bigger than or equal to 1, we get no loss. If it's smaller than 1, we get loss that grows linearly. And so how can we, well, we know then that from this equation here that we can bound that this is greater than or equal to 1 minus hinge loss applied to ui dot w star, right? We proved that before. And so now, if we sum this over all mistakes that we make over the course of the algorithm, we get that w dot w star is greater than or equal to, well, it grows by, so let's just write this out, equals w dot w star plus 1 minus h of ui dot w star, right? And so it grows by 1 every time. So that gets m summed over m examples. But then it shrinks by sum over mistakes. I'm running out of room here. Let's. I'll write it here instead. So we'll write w dot w star winds up being then greater than or equal to m minus the sum over errors I of h of ui dot w star, right? And this is what happens. This is the growth in terms of all of the places where we make an error. On the places where we don't make an error, we get that. So this is on error. This is on no error. We'll get that w new dot w star is equal to, well, w new is the same as w if we don't make an error. So it's equal to w dot w star. And it's greater than or equal to w dot w star minus h of ui dot w star. Why is that true? Because h is bigger than or equal to 0. So if we subtract it, we can only make it smaller, right? And so now, if we sum over all trials, right, we'll get m on all of the trials where we make an error. We'll get minus h of ui dot w star on all trials where we make an error, but we'll also get h of ui dot w star on all trials where we don't make an error, right? So there's an extra term here, sum over correct I of h of ui dot w star, right? And so bringing that all together, w dot w star is bigger than or equal to m minus sum over all trials I, h of ui dot w star. Okay. Yeah. All right, so what does that mean? Oh, I guess we had a name for this sum, right? We gave it a name up here, right? So it's w dot w star is bigger than or equal to m minus l star, right? And so now, just like before, we can put everything together, right? And so we'll have that m minus l star is less than or equal to w dot w star, which we can do Cauchy-Schwarz inequality. Sorry, w dot. Yeah, Cauchy-Schwarz inequality. So that's less than or equal to the norm of w times the norm of w star, which is capital W. And then the norm of w now is again square root of m or less, which is, so we have less than or equal to the square root of m times w, right? So before we had just that m is less than square root of mw. Now we have that m minus l star is less than or equal to square root of mw, right? So it's a slightly looser bound, right? If l star is equal to 0, it's the same bound. If l star is bigger than 0, it's a slightly weaker bound on m. It turns out I'm not going to solve it here because it's just annoying and not particularly enlightening, but we can turn it into a bound that looks like this. So this turns out to imply that m is less than or equal to w squared plus 2l star, right? So this is the final conclusion. And before we had that m was less than or equal to w squared. Now we have w squared plus 2l star. Okay? So again, it's not a very complicated proof. It fits all on one slide. But this time it allows us to handle the case of errors, right? And it still allows us to prove a bound on the total number of mistakes that the perceptron algorithm is going to make, which is pretty cool. The difference, of course, is that if you're not linearly separable and you keep getting more and more examples, L star, the best possible separator, the performance of the best possible weight vector, L star is going to keep getting worse and worse, meaning bigger and bigger. And so we can keep making more mistakes forever as L star grows, but this bounds the rate at which we can make new mistakes, right? We're never going to make mistakes at a rate bigger than 2L star, except for like a little period at the beginning when we might pay according to the norm of the W star squared. Okay. So this is the limit of proofs about the perceptron. I'm sure you're very sad that you won't see more slides of equations like this one for at least the rest of this lecture. Do people have questions about either of these two proofs? Yeah.
I can understand why W dot W star is large or equal to m minus the sum of h.
Mm-hmm, right. So the question was, why is W dot W star satisfy the bound that we proved for it? So let me go over that argument again. So the first thing that we did, right, was we analyzed the behavior on an error. Let me switch to a new color so that I can annotate this. Oh my. Here, let's do this again, and we'll make it a new color. There we go. All right, so we analyzed it two cases separately, right? On error, right here, and on no error, right here, right? And on error, W dot W star, well, W new is W plus UI dot W star, and you split that up into W dot W star and UI dot W star, right? And you get, based on this inequality here, right, you get this bound here, which turns into that. So you're okay with that part, right? On no error, you get w nu.w star is equal to w.w star. And just to make things add up nicely, we're going to put minus h of ui dot w star here, which we can do because we're subtracting something positive and only making it smaller, right? So now if we sum that over all trials, well, on trials where we get an error, we'll get a minus h of ui dot w star, and on trials where we don't get an error, we'll get a minus h of ui dot w star. So in the end, we'll get the sum over all I of h of ui dot w star, right? And then the remaining terms on trials where we do get an error, we'll get a +1. On trials where we don't get an error, we don't get that +1. And so the sum over all trials will be just the number of errors.
So where is the w dot w star? Before the +1.
Oh, right. So this is on, so the question is, where did w.w star go? And what I did was I analyzed what's happening over all iterations summed together, right? So on each iteration, it grows by this much, right? So w.w star increases by these two terms, the 1 and the minus h of ui dot w star, right? And so over all terms, it starts at 0, and then the sum of all of the increases is a bound on how big it could get, right? So if you wanted to prove that formally, you'd do it by induction. So I did essentially, I skipped over a proof by induction that would hold over the entire sequence. Yes?
So you made a comment about how L star can grow, and I didn't understand that.
Oh, right. So L star is it's the sum over all training examples, right, of the hinge loss of the optimal predictor, of the optimal weight vector.
Oh, you're saying as you see more examples.
As you see more examples, L star is going to grow. That's all I was saying. And so the point is, if you know ahead of time a bound on L star, then this puts a sharp bound on the number of mistakes we could get, right? It's this much. But if you don't know that bound, you're just saying, well, I think it's that L star isn't going to go too quickly training examples, then what this bound gives us is a bound on how rapidly our own number of mistakes can grow, right? More questions? Yeah.
I don't remember well. What's the difference between an error and a margin error?
Right. So an error is when we classify an example wrong, right? It's when we get it on the wrong side of the decision boundary. A margin error is when we don't get a large enough margin. In other words, so we're supposed to satisfy the constraint ui.w is greater than or equal to 1. And if we fail to satisfy that constraint, that's a margin error. Right? Here we're actually counting errors, though, not margin errors. Yeah.
Even if we classify correctly?
Even if you classify correctly, right? So a margin error is, you get more margin errors than you do errors, right? A margin error is like, I'm doing well, but I'm not doing well enough, right? And so it turns out that margin errors are important as a concept to analyze algorithms that we're going to be looking at in the future. More questions? All right. So at this point, at least if you either followed the proof or believe me that the proof is correct, you should be convinced that perceptrons can actually do quite well on data that's either separable or pretty close to separable, right? Meaning that L star isn't too big. Which is kind of cool, right? It's an incredibly simple learning algorithm, and yet it provably works with essentially no assumptions on the distribution that's generating your data, right? The only assumption you make is that there exists a weight vector that performs well. So that's kind of cool, right? And that's typical of empirical risk minimization, that you'll wind up being able to prove results with very few assumptions, right? Sometimes you'll wind up getting weaker constants than you might get for a similar algorithm that's based on stronger assumptions. But I'm always willing to take a slightly worse set of constants in return for not having to make assumptions that I don't believe. Right? Yeah.
So I think
Right.
You transfer that, convert that to this system by choosing a case where gamma is equals to the minimum of the UI times.
That's right. So we went from something that was just linearly separable, meaning that it satisfied ui.w greater than 0, right, to something that was separable plus a margin, which means that ui.w is greater than or equal to 1, right, for some w, and then the norm of w tells you what that margin is.
Does this mean they choose the error rate of the margin error?
Right. So by scaling w star, you can make a trade-off. You can if you scale up w star, you could potentially make some of the margin errors smaller, but you would wind up making the margin itself smaller as well, right? So you can trade off sort of where do you place the margin versus how much do you charge against each margin error. All right. So these are some good questions. So keep them coming. Yes?
Can you make a comment on how it compares to methods we've seen already?
Yes, I can make a comment on how it compares to methods we've seen already. I guess the two main ones that we've seen already are logistic regression and the Bayes classifier, in particular the Gaussian Bayes or Gaussian naive Bayes classifiers, right? So all of these classifiers make linear separators, right? And different ones get those separators by a different algorithm, right? And so you might expect then that they have different performance under different circumstances, right? They're going to, in the limit, if all of their assumptions are satisfied and you give them tons of training data, then they're all going to do well. But in the more usual case where some of the assumptions aren't satisfied or we don't have a huge amount of training data, the performance is going to be different, right? Can anybody give me a thought on what might perform out of those three algorithms? Let's say Gaussian naive Bayes, logistic regression, and perceptron. What might cause one to perform better than another?
Whether or not some of the assumptions of the models are being violated by the data.
Right. If, for example, our independence assumption is violated, it could cause the naive Bayes classifier to do very poorly, right? Or if the assumption of linear separability is badly violated, the perceptron could do quite poorly, right? There's also going to be differences in how expensive they are, right? So if you remember, Gaussian naive Bayes was incredibly cheap, right? We just summed something up over all of our examples, and we were done. Perceptron is just as cheap as Gaussian naive Bayes. Logistic regression, as those of you who were hitting our server over the weekend found out, is substantially more computationally intensive, right? So that could be a problem or it could not, right? If you're Google sitting there with a clusters of tens of thousands of machines, sure, throw a logistic regression at it. Why not, right? But if you have a billion features, maybe even a big cluster gets brought to its knees, especially if you try and use one of the fancier algorithms to optimize logistic regression. All right? So that's basically the answer, is that under different circumstances, different assumptions about the data, they might be faster or slower and might perform better or worse.
So the hardest intuition to get, I think, is for logistic regression of what the assumption actually means.
Mm-hmm.
It's like you say, okay, well, we assume the logit function represents it well, but you couldn't tell from a data set.
Right.
Should I expect, should the default be logistic regression if I don't know much about the data set?
That's a good question. Logistic regression is a pretty good default. If you don't know much about the data beyond thinking that you have a set of features that make it moderately close to linearly separable, there are a lot worse things you could do than run logistic regression on it. Perceptron is cheaper computationally So for very large scale things, perceptron might be better.
But converges slower in practice.
I mean, so if you actually write out the algorithms, gradient descent on logistic regression and the perceptron algorithm look almost the same, right? I'm not going to go and write them out. And so they're going to perform almost the same if you do like online gradient descent on logistic regression versus perceptron algorithm. Online gradient descent on logistic regression might actually perform slightly better because it's smoother around the region where you're making classification errors. But to prove that actually would go well beyond the techniques that we've discussed so far. You would actually want to do a sort of amortized analysis on that online logistic regression algorithm in order to prove it. And people have done that analysis, and it's in the literature, but I'm not going to drag you through it. And then if you do a fancier optimization algorithm on logistic regression, you could expect that you make better use of your training data. But if you're in a situation where you got plenty of training data, there's no point in doing that. More questions? All right, so those were really good. That's nice to, those are nice questions. So the next thing that I want to go to is something called a margin perceptron. And in a margin, okay, so in the ordinary perceptron, right, we did an update if our weight vector satisfied ui.w is less than or equal to 0, right? And now what we're going to do is update, right, we update if we made an error, right? Now we're going to update if ui.w is less than or equal to 1, right? In other words, if we made a margin error, right? And the update is going to be pretty much the same. W is equal to, I guess we'll say colon equal for assignment, for those of you who like Pascal. W plus UI, right? Except that now, before it didn't make a difference, like the perceptron, if you scaled the weight vector, it didn't change the decision surface. Now we're going to, the actual size is going to make a difference, and so we're going to add a learning rate eta. Right? And so it's going to be the same update as the perceptron, except that now it makes sense to have a learning rate that scales the update. All right. So, so why did we just do this? It's a good question. The benefit of the margin perceptron is that instead of finding a separator that has few errors, we're going to find a separator that has few margin errors, right? So in other words, before we assumed that there existed a separator that had good margin, but the perceptron wasn't necessarily going to find it, right? Whereas the margin perceptron, if you assume that you have that there exists a separator that has good margin, the margin perceptron will find a separator that has good margin. Right? So it gives you a slightly stronger conclusion. So why do we care about getting that slightly stronger conclusion? At the moment, we don't. But later on in the course, in about a month or so, we're going to get to a section where we're able to prove generalization bounds for large margin separators. So what that means is that we could run the margin perceptron, get a large margin separator, and hand that vector of weights to somebody, and be confident that those weights are going to do well. Whereas with the perceptron, if we wanted to hand something to somebody, we'd have to hand them the whole state of our perceptron algorithm and tell them to keep updating their weight vector, right? And then we'd know that if they kept running the perceptron algorithm, they'd keep making few errors. right? Which is a little bit less convenient for them. It's a little bit harder to code into a piece of software that you ship out to 1 million iPhones, right? So if you want to actually just encode the result of your learning as a weight vector, you probably want to do the margin perceptron instead of the perceptron. Okay? The analysis, I could go through the analysis of the margin perceptron, but at this point it would look incredibly familiar to you. It would be the exact same sequence of steps. We'd pick these two quantities, w.w star and the norm of w. We'd analyze how they change over time, put bounds on that, and solve those bounds to get a bound on the overall number of mistakes we make. Rather than do that, I'll just give a spoiler. The margin perceptron has few margin errors under the assumption that there exists a W star that has low empirical risk. Yeah?
Should the U and W be normalized here?
Right. So there's no, this algorithm, it's correct as written. You don't have to make any additional normalizations. If you want to analyze the algorithms, you might decide, for example, to compare yourself only to weight vectors W star up to some maximum norm, right? Just like we were doing in the previous slides. So you can, if you want to, normalize every example, right? Divide it by its norm to make it unit norm. And that might or might not improve the performance of your algorithm depending on whether normalizing your examples makes them better separable or worse separable, right? Which is a property of your data. It's not something that I can give you general advice on. Okay. All right, so the margin perceptron, almost the same algorithm, but it winds up giving you, in the end, a large margin separator instead of just a separator. Okay. So, I should say, by the way, this learning rate, right? So how would we pick it? Well, a decent way to pick it is if you think that that there exists a weight vector of norm no more than W that does well, and if you think that you're going to get n examples total, a decent way to set it is to have it be proportional to W over the square root of the number of examples, right? And again, if we do the analysis, we would be able to prove that, but I just wanted to mention the result and drag you through the analysis. Okay, so this is what going to make that comparison that you asked about earlier. We've given you a whole bunch of different ways of learning a linear separator. We're going to give you one more in another lecture or two called a support vector machine. All have the same form of their separator, all have different optimality criteria, right? Things that we're optimizing. So, so which is best? The answer is none of them, right? Each one can be best in different circumstances. For example, if you have tons of data and very few features, you might want to do something like logistic regression. Or you might want to do a batch optimization of a margin perceptron, which is very close to doing logistic regression. If you have lots of data but lots of features, well, having a ton of features rules out doing exact optimization of something like a logistic regression, right? Like you might run Newton's method, for example, but Newton's method is quadratic in memory in the number of features, and that's prohibitive if you have 1 billion features. So what you would do then is have like an online optimization style algorithm, like, for example, the perceptron, or like online gradient descent of logistic regression. If you have little data with lots of features, then something like a perceptron or like logistic regression would likely overfit, right? You're learning a ton of parameters with very little data, and so you might do that makes stronger assumptions and hence doesn't overfit as much, like, for example, Gaussian naive Bayes. And often in the case where you have a ton of data, very few data with a ton of features, the Gaussian naive Bayes is as good as you're going to get. And then if you have not so much data and very few features, well, first, you're mostly sunk, right? But if you really have to get the best possible performance out of that, I would say use none of the above. I would say to make some very informative Bayesian prior over what your classifier should be, and do the full Bayesian calculation, meaning integrating over all of your prior posterior, right? Integrating everything out so that you get the exact distribution over weight vectors. And that will be sort of the best use of a small amount of data, but it will be the most computationally intensive. But if you have, 10 data points with 10 features, you don't really care so much about doing things like even an exponential time algorithm would be just fine for that case. All right. So, so that's the end of what I wanted to say about perceptrons. We're going to move on to something about ordinary perceptrons anyway. We're going to move on to something else. Before I do that, any questions about the whole of perceptrons? All right, you guys are all perceptron experts by now. Excellent. OK, so now we get to something else. Suppose that, all right, so in the perceptron algorithm, right, suppose that I had a bunch of positive data points over here, right, and a bunch of negative data points over here, right, and this is my feature x, right, and those are my class labels. And so I'm going to wind up learning a discriminant function, right? It's going to be something that looks like this, right? It'll be a linear function, w dot x. Here's the origin, right? And hopefully, it's going to be positive on the side with the positive examples and negative on the side with the negative examples, right? So that's great if that happens to describe your data. What if your data happen to look like this, right? We have some positive examples here, some negative examples here, and then some more positive examples over here, right? This is a bad situation for your poor old perceptron. Because there doesn't exist a linear separator that performs well. Instead, what we might hope, right, here's our feature vector, we might hope to learn a separator that looks something like this, right? Quadratic function, which is bigger than 0 at the positive points and smaller than 0 at the negative points. Okay? So what do we do in order to do that? Well, what we want to do is change the set of features that we're using, right? So before we had just x as our feature, right? And to learn a quadratic, we might change it to a vector, 1x squared, right? So this is a transformation I can make on every example, right? I can say for I equals 1 to n, example I is equal to gets assigned to be transformed example I, right? And it changes what the perceptron can learn, right? If you change the representation of your data, you're going to change what it is that the perceptron can do for you, or any other linear discriminant function. Okay? So looking at this data, right, if we did that transformation, say we did the transformation from just x, right, to x and x squared, right? So instead of having them arrayed along a line, they would be arrayed along a plane, right, like this. Here would be x, and here would be x squared, right? And so I would have the negative examples like this near the origin, and the positive examples going up like this, right? That makes sense? Everybody sees that that's what would happen with the transformation. And so now, if I do a linear separator, let's say I allow myself a bias term, I can put a linear separator right there, right? And that linear separator has perfect performance, even though it was not possible to linearly separate our data before, right? So that just shows the importance of doing a feature transform. So in general, in machine learning, it's really important to be able to do feature transforms. This one of making polynomials out of your existing features is a pretty good one. right? It lets you do things like decision boundaries that are conic sections, things like parabolas or ellipses, instead of lines, right? So if I take this, if I take the decision boundary in the quadratic case and I map it back down here, right, I get a decision boundary that has 2 thresholds instead of 1. You'll see throughout the semester probably a bunch of different feature transformations. It's always important, right? This is one of the main places where your knowledge of your data set comes in, right? If you know your data set, then you can get intuition for what feature transforms you might need to make on it in order to be able to make it closer to separable. Okay? So that's what happens if you just do feature transforms. I want to go even farther than that. Suppose that we consider our, okay, we have some examples, right? Plus, 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 minus, minus, plus, minus, minus, plus, 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 right? And so we want to learn, we want to be able to get a discriminant function, right? A discriminant function is a function that's positive on the positive examples and negative on the negative examples, at least up to some error, right? And so, you know, looking at that, I don't know what the right form is for my discriminant function. But what if I tell my algorithm that it's supposed to learn the entire discriminant function, right? Not just, you know, assume that it's quadratic, right? But just say, out of all of the functions in the world, pick me a function that's a good discriminant function for this data, right? So what's the first thing that we should worry about when I say that? Overfitting, right? So that gives my algorithm a huge amount of flexibility, right? I could pick a discriminant function that was like this, right? You know, a spike there, a spike there, a spike there, a spike there, right? And so forth, right? And that function, I'm going to almost be willing to guarantee you that it's not going to generalize well, right? But let's leave that aside for a moment, right? Let's, there's maybe even a conceptual difficulty, right? How do we tell our algorithm that it has a whole function as one of its parameters, right? I can't put a function in my computer's memory, or at least not very well, right? Like there's an infinite amount of information in your average function, and I don't have an infinite amount of memory in my trusty computer here. So what are we going to do? So one thing to think about is suppose that we thought of the function as a vector, right? So if we have a function, let's say f of x is equal to x squared minus 2x plus 1, right? So if I plot that, right, it's going to look like, I don't know, something like this, right? And that's an infinite amount of information. But what if I say, well, OK, I don't quite care about having an infinite amount of information. I just want a lot of it, right? So what I can do is in MATLAB, I can say something like, you know, x's equals 0 colon 0.01 colon, sorry, my handwriting is getting worse than usual. 0 colon 0.01 colon 5, right? And then f's is equal to x's squared plus 2 times x's plus 1, right? And now I have a vector f's has 501 points in it, right? 501 components, because I sampled every hundredth of a unit from 0 to 5. And it's not exactly the same as that function, but it's a pretty darn good representation of that function, right? So I could say, OK, maybe that's what I'm going to try and learn, right? So I'll pass to my Perceptron algorithm a representation that lets it learn functions in that representation, right? And if I do that, it's going to immediately come back and do that, right? Like if you go through and think about it, you know, let's say I go through and I make a mistake on an example at 3.27, right? well, then the perceptron algorithm will take the value of the function at 3.27 and move it up by 1 in order to make me less likely to make a mistake on that same example in the future, right? And so that was a bad idea, right? But it's going to turn out to be the basis of a good idea. All right, so I can think of this as being a particular kind of feature transformation, right? So if I take my feature x and transform it so that I have a feature that tells me is 0 less than or equal to x less than 0.01, right? And if that's true, 1, otherwise 0. Another feature that says is 0.01 less than or equal to x less than 0.02, right? And that can be 1 or 0, and so forth. And I have 501 of these, right? And you can work out in your head that if I do this feature transformation and then feed it to the perceptron algorithm, it's going to do essentially this thing right here, right? So it didn't help us to go to finite but large. What happens if we go all the way to an infinite representation, right? We think of these functions as being an actual infinite amount of information, right? So it's going to turn out that we can do that. We can write down the math that lets us derive the perceptron algorithm in this case. The key idea is basically going to be to look at vector spaces that are infinite dimensional, right? So you can think of the collection of all functions as being a vector space, just like Rn, but with infinitely many dimensions, one dimension for every argument to the function. Just like here, what we're doing is one dimension for every rounded off argument to the function, right? And so I'm not going to get into it this lecture because that would be a little too mind-blowing for 3 minutes. But when we come back on Wednesday, that's what we'll do. We'll look at infinite dimensional perceptron algorithm, and we'll see that we can actually implement it on finite computers, and we can actually prove that it performs pretty well. See you on Wednesday.